In today's video, we will discuss about total internal reflection, or in short it is called TIR. So here you can see that in total internal reflection we are considering two medium. One is optically denser medium, the other one is optically rarer medium. Okay, let us focus in this diagram first. So this is optically denser medium, optically rarer medium. Light ray is travelling from denser to rarer medium. This is the normal drawn at the point of incidence. And here suppose we are considering the first ray. First ray is this one. So when this ray moves towards the other medium like this, then what we know that it will bend away from the normal. So this is the incident ray, and refracted ray is this one. Okay, see here also I have given number 1, that means this is ray number 1. Similarly, if you increase the angle of incidence, now we are giving the ray in this direction. Okay, so that means the angle of incidence has increased, and at the same time the refracted ray will bend more. Okay, so here you can see that I have denoted it by 2. So this is 2, this is also 2, so that is the same ray. Okay, now again, if I am increasing the angle of incidence further, suppose this ray 3, like this, it goes more away from the normal, so it reaches exactly at the interface of both the medium. So in this particular case we can say that what is the angle of refraction, because the light ray is exactly at the interface, the angle of refraction is 90 degree. Okay, so if the angle of refraction is 90 degree, then its corresponding angle of incidence, that is this angle which is given by IC, is called critical angle. So remember that in total internal reflection we have got a term that is called critical angle. The meaning of critical angle is that it is nothing but it is the value of angle of incidence. In this case, which angle of incidence? This one, IC. And which ray is making this angle? Ray number 3. Okay, so critical angle means it is the value of angle of incidence for which the angle of refraction becomes 90 degree. This is ray 3, this is also ray 3, exactly at the interface. Now if you increase the angle of incidence beyond critical angle, that means now if we allow ray 4 to move, now you can see that ray 4 is making more angle than critical angle, more than the critical angle, right? So if this ray 4 is allowed to move, where will it go now? Because for ray 3 we got the refracted ray exactly at the surface, so ray 4, the refracted ray must come back then, right? So in this case if you see nicely, it looks like a reflection, ray 4 going this way, then it is again coming back to the first medium, right? So this is called total internal reflection. This is actually what was happening here. Initially refraction was taking place, but as soon as we crossed this critical angle, we got a kind of reflection. So this is called total internal reflection. So I hope it is clear that the definitions of this one, critical angle and total internal reflection, I have written here. So another very important thing, that total internal reflection, what are the conditions, under which conditions this total internal reflection will take place? So basically there are two conditions. One condition is that refraction must take place from denser medium to rarer medium. That is one condition. Another condition is that the angle of incidence must be greater than the critical angle. Okay, because ray 3 is making critical angle, but ray 4 angle of incidence is more than critical angle. That is why we got the light ray coming back to the first medium. Okay, so these are the two conditions for total internal reflection to take place. Now the definitions of critical angle and TIR I have written here. Critical angle I have written that when light moves from denser to rarer medium, for a particular value of angle of incidence, the angle of refraction becomes 90 degree. This value of angle of incidence is called critical angle. And total internal reflection I have written, when refraction takes place from denser to rarer medium, for angle of incidence greater than critical angle, light ray comes back to the first medium, and this process is called total internal reflection, or this phenomenon is called total internal reflection. Okay, So there are many phenomenon which is based on this principle, like mirage, you know about it. Another phenomenon is there, these are naturally occurring phenomenon like mirage. Then looming is another phenomenon. Well, I will tell you about mirage and looming a little bit, but not in this video but in next video. Okay, so after this there is a mathematical treatment with related to total internal reflection, this part. Okay, now as we got that ray 3 in the previous diagram, ray 3 what kind of situation it was creating, the thing is like this, no? Ray 3, how much is the angle of incidence, critical angle, and how much is the angle of refraction for that, it is 90 degree. Alright, so this diagram I have just drawn here. Alright, now for this particular case, if we apply Snell's law, then angle of incidence will be equal to what? Critical angle, and angle of refraction will be equal to 90 degrees. So if we use Snell's law, sin IC by sin R, because actually it is sin I by sin R, but I is IC, so I have written IC. That is equal to mu RD. RD means this is which medium? This is the denser medium. This is the rarer medium. So when we write mu, what we write? Mu 2 1. 2 1 means second medium with respect to the first medium. Here second medium is the rarer medium, so I have written mu RD. Rarer medium, mu RD means it is the refractive index of rarer medium with respect to the denser one. Alright. Now sin R, in this particular case sin R is how much? 90 degree. So sin 90 will be what? 1. Okay, so that means sin IC by 1 is equal to mu RD. But remember that whenever we establish a relation, if I simply write here mu RD, this mu RD represents refractive index of the rarer medium with respect to the denser. But whenever we establish any relation, we prefer to keep the relation in such a way or in such a form that it relates mu of denser medium with respect to the rarer. So for that RD we have to convert it to DR, and if we take the reciprocal in right hand side, in left hand side also we should take the reciprocal. So sin 90 should go up, sin 90 goes up and it becomes what? 1. Okay, and once this sin IC will come down as we are taking the reciprocal in left hand side as well as in right hand side. So this is our required equation, 1 by sin IC is equal to mu dr. In some book in place of IC you may get theta c also, same thing, that is also represents critical angle. Okay, then application of total internal reflection, very important thing, this one application, it is optical fiber. So optical fiber means we know that it's a fiber, it's a glass tube having very small diameter, very small. So this optical fiber, it transmits light from one point to another without reducing its intensity. Okay, one point to another without reducing its intensity. So this is a kind of tube like thing. Okay, it's like this kind of thing. Okay, just a second. Okay, tube like thing, it is something like this. Okay, then this tube, it is covered by two parts. This material, this is called core material, the material which is making the tube, that is the core material. Just above core there is another coating, this coating is there, and this coating is called cladding. I have just drawn it here. Here you can see this part. Okay, there is the core material, this part is the core having a refractive index of nearly 1.5. Then around that core, core, there is another coating, that is cladding, this part and this side, this is the cladding. Refractive index of cladding material is nearly 1.4, and above that another coating is there, that is called protective jacket. Protective jacket. So protect, it is not clear here, but you can write it protective jacket or protective sheath. So this protective jacket or protective sheath, it protects the optical fiber from any external, you can say external factors. So this optical fiber, we know that it works on the principle of total internal reflection. And how it works? See, if the refractive index of the cladding material is 1.4 and core material is 1.5, when light is allowed to fall on the core material like this, okay, it has a tendency to move from core to cladding, that means from denser to rarer medium. Denser, why? Because core is having more refractive index 1.5, cladding is having less refractive index, so it has a tendency to go from rarer to, sorry, denser to rarer medium. So there is a possibility of a total internal reflection, because we know that for total internal reflection we have two condition. One is light has to move from denser to rarer medium, so this thing is happening here. Now if you just draw one normal at this point, this angle is nearly how much? Angle of incidence is nearly 45 degree here. From the diagram it is clear, 45 degree. But for this material, IC means critical angle is 41 degree. So angle of incidence is now what? More than critical angle, because critical angle is 41 degree, angle of incidence is 45 degree. And I told you already that for total internal reflection, another condition is that the angle of incidence must be greater than the critical angle. So it is happening here. As a result, what will happen? This incident ray, it will not undergo refraction this side, but it will undergo total internal reflection. So it will come back like this. It will come back like this. Again at this point total internal reflection will take place, then it will go like this. At this point total internal reflection will take place, it will go like this. So the light ray is following a zigzag path and without transmitting. Without transmitting means, see, light ray is not neither going this side nor going this side. So that means what? The intensity of light ray will not be reduced, it will be trapped inside the optical fiber. It will go like following a zigzag path and it will reach to the destination. Okay, so this is the main you can say main application or main way how this optical fiber works. So in which purpose this optical fiber is used? One purpose is telecommunication. In telecommunication purpose this optical fiber is used. Then another use is there, that is in endoscopy. In endoscopy we know that this optical fiber, it helps light ray to move to such a place where it is difficult. In other way we cannot take light to that particular place inside our body, right? Endoscopy. So how this optical fiber works there, it without diminishing the intensity of light, it can carry light to a particular point of our body, so that while taking the image of this particular internal organ, we get enough light. Okay, so in this way this endoscopy is carried out, and these are the two application of optical fiber. And I told you that total internal, some other applications are also there, you can go through those applications. And regarding this total internal reflection, this is how we use total internal reflection in a constructive way. But there are two natural phenomena, as I told you, mirage and looming, where this total internal reflection is also used. So in next video I will just briefly I will discuss about this one, mirage and looming. Thank you.